received the Best Paper Awards at DAC, ICCAD, Micro, ASP.DAC, and MLCAD. He's an IEEE Fellow and served as General Chairs for ISPD 2012, MLCAD 2024-25, and is the Editor-in-Chief of ACM 2 Days.
Yeah. So the title of my presentation is Physical Design for Systolic Array-based Integrated Circuit. And the concept of a systolic array was started in the late 1970s by Hu and Licensing. And there are two key ingredients for systolic array. One is there's one regular array of processing element, and also there's no global interconnect. And nowadays we typically see this 2D array. But if you will look at one early work, by Kong and Licensing, this is one picture they show. This is a more, hexagon, type of systolic array. This is to show how to use this type of systolic array to do matrix multiplication. And so the input data pumped into the circuit, and the circuit output like at a heartbeat, pump the data out. So it's what's called systolic array. And so after several decades now, systolic array got popularity again because of the AI and machine learning and computation. Okay, so one popular architecture is it has one key array. This is a 2D regular array, and each processing element is mostly as a map unit, multiplication and accumulation. It also has a local register file. And so if we look at the overall architecture, this is off-chip DRAM, global buffer. You can think of a scratch pad memory or SRAM, and they're connected with 5-in. And you'll see there's also a control logic. And because of the popularity of in the machine learning computing, so systolic array received a lot of research attention, but mostly in the front end. So in architecture design, on workload mapping, scheduling, and the algorithm power code design, and also high-level synthesis, and in particular audio assay, that is automatic systolic array synthesis developed by Professor Jason Hunt. But if we look at the physical design, there are very few works about the physical design about AI's accelerator, and here we look at the layout issues for systolic array. And here I will summarize our recent works on how to exploit the regularity of systolic array for better layout design. So the first one is the mixed size placement. In this problem formation, we treat each PE as a hard macro, and there are other dust cells, like those control logic. So this approach consists of two phases. One is the PE placement, P placement. First, we cluster those dust cells to its PEs, so we call it C3 macro. So we showed on top right here. So this is one PE, and these are dust cell. So C3 means chocolate covered cherry. So this is what we're putting them together. Okay. So then we got like this C3 macro. So then we do a C3 macro placement, and after that we fix the PE location, and then we disassemble those dust cells and place them. So this is the overall flow. So the first step is to do the clustering. So we adopt one previous approach to cluster those dust cells that are those have tight connections with the PE, cluster them together. And the reasons is that we're going to use that for space reservation. So now when we do this C3 macro placement, each C3 macro, and actually its area is the P area plus the clustered cells. So this is for space reservation. Okay. And at this moment, when we do this placement, we leverage the regularity because this is a 2D array. So the order is pretty much decided. We just follow the order of a schematic. And so then we can easily apply linear programming instead of nonlinear programming to solve this problem. And actually we use like two passes of linear programming. I will skip some details. Actually this work was published in NCCAD last year, so there's some details I skip. Okay. And after that, we fix the locations of the PEs, and then we release all those dust cells to replace them. And those dust cells, first we have an initial placement according to the force balance by the net through those PEs, and then we run replace, and the final legalization and the detail placement is through NTU place. Okay. So here I like to highlight some key results, and so the light blue bars is from our result is sysmix, and we compare one commercial to and auto PNP, and number 10 reference. This is recent work by Professor Libolin's group. And first, let's look at half parameter variant, and from this different cases. And actually, the difference actually can be huge. So one reason is that the other works are their general purpose mixed size placers, and our is customized. It's not exactly fair comparison, but just to show you, actually there's room for this. If you have customized the physical design, you can get good improvement. And also, if we look at the runtime, and our runtime is so much shorter. Actually, it's hugely shorter than the commercial T and auto PMTP. And it's pretty impressive that it was place actually is still much faster than ours. Okay, just to show you the room. Okay. So this is for the one problem formulation that we assume, where we assume each P is a Han macro. Actually, we did another work. We released that assumption. In that assumption, we assume all the PE, the gate in the PE are dust cells. So this is a flat cell placement. It's not mixed cell placement. And in this case, so this is the results, and we compare pacer is from our approach. We compare with the replace and NTU place and the powder. Powder was published in 2013, and especially reference 9. I like to emphasize that because when we talk about regularity, like one previous related approach actually is data path placement. Data path placement also has 1D regularity, but the problem nature is somewhat different from systolic array. And here, reference 9 actually is by Professor Jiang Hu on the data path placement. So we can here the variant actually, this is not the half parameter variant. This is the global routing variant. So it is more accurate, and so we can see that compared to replace, we can reduce the compare all these methods, except the data path one, we can reduce the global routing variant by about 10%. That is quite significant. Again, I'm not saying this is very correct because we're customized. They're mostly general purpose. Again, to show you there's a room, that we can benefit from. Okay. And next, I will move on to apply this to FPGA placement. So FPGA placement, the problem is quite different. So here, like, if we look at the systolic array architecture, that is the same as before, but the underlying architecture is different. And so if we look at the computing unit of FPGA, say, here I'm talking about the conventional, like our DSP columns and lookup tables. For PEs, normally we map them to DSP columns because we have a multiplier, so we can leverage the computing efficiency of a DSP. I'm not showing here, but some more update is like AMD, they have a newer FPGA architecture with the AI engine that is better architecture. We're trying that, but we don't have a result yet. Okay. And so then the problem is that given like one systolic array on the right, we need to place them onto DSP columns on the left. This figure is not a good one, and the reasons is that the systolic array, typically the aspect ratio is more squarish, so the number of rows, number of columns, similar, not too much in general, okay. But if we look at FPGA architecture, we have only a few, narrow and tall columns. So pretty much we needed to partition the systolic array columns, into partitions and pack multiple systolic array columns into like a one DSP column. So that is the one special problem. Okay. So how to do that? I will show like we have like a several-step approach. The first step is to do the partitioning of those systolic array columns, and this is systolic array is a 3x5. So I will show that we use a color to represent a different candidate for partitions. So the first one, pretty much we say, hey, we pack all the columns into one DSP column. The second one, say we partition it into a 2 DSP column, and the last one we partition into 5 DSP columns. And so you may ask, hey, there are so many partitioning like options. What do we do? Okay. So the first step actually is we enumerate all the options. Okay. And next we do pruning. So how to do the pruning? And for each partitioning candidate solution, actually we can calculate the upper bound and the lower bound of place half parameter variant. I'll skip some detail. We have some. So this one is published in ICCAD 2023. Okay. So then once we get upper bound and the lower bound, the pruning is done by, so suppose like one candidate is the lower bound half parameter variance is greater than the upper bound than another solution, then that's obviously worse. We can get rid of that. So after those pruning, then we have only a few candidates left. And for the remaining candidates, what we do actually is we place all of them. And after we place all of them, we just pick the best one. Okay, you may ask place all of them. Would that be like a too time-consuming? The answer is no, because our placement is super fast. So here I'll just show you so after you do the partitioning, the idea is how to map one partition into one DSP column. So our approach is analytical. So it's called RSET. So that is region-wise swap in alternating direction. I will elaborate in later example. So here, this array, actually, it is only one partition. Okay. On the right, that is one DSP column. Okay. So for each partition, we divide it into 7 different regions, and these are indicated by the 7 colors. And the placement location of these regions in the DSP column is showing on the right. Okay, so you see the red partition is the lower left, the yellow one is at the top. We just follow that one. Okay. And the next question is that for each colored, region, how to place that? Actually, this is the first. We just do swapping. Okay, so in this example here, each square we have a number. This number tells the index location in this vertical DSP column. So 1 is we place it in the lowest location, 2, 3, 4, and so on. So you see the order actually is alternating swapping 1 to vertical, horizontal, we just do like that, So this is why you see we don't even do any optimization. We just follow this procedure, Okay. And there are some other details. So for example, like how to cut those regions. There's a parameter. We have a method to search that. And because of that, this process actually it is super fast. It is pretty much like here I use animation to show. Actually, there's an analytical formula. You just plug in, immediately know the location of each PE. Okay. And so if we look at this this one partition, now we just look at one partition. We compared with the ILP solver. Actually, our approach is better than ILP solver. And if we look at the horizontal axis means the distance between two neighboring DSP columns. And here we try to map like a 1 8x8 array, right? Okay, so we look at the warland, and normally we take ILP result as golden, but if we look at our result, blue one, and when the circuit size, it often beat ILP solver, and also it is much faster. And to get this result, ILP sometimes may take hours, so we just take seconds. Okay. And so this is the overall like a circuit comparison results. And the first section we evaluated on different FPGA architectures. We compared with Vivado, and the first two columns, that is Vivado result. The second one is our method plus Vivado, because we only do the macro. The dust itself is still done by Vivado, so we can tell that we can reduce the warland by 20%, and the middle and the right column we compare with other methods. We can also reduce 20% to 40%. That is quite significant. Again, I just because we're customizing, so this is the approach. And this one has more results. We play with timing-driven placement, and we compared. The blue one is from our result, and the first row is the half parameter warland. So we compare with Vivado, we achieve over like 20% warland reduction, and the second row is route utilization, and this is the third row is the CPU time. So when we apply our method with Vivado, most runtime is Vivado. The runtime of our macro part is negligible. It's almost nothing, and it also achieves better timing results and less worse negative slack and better frequency. Okay. So this is the placement part. So I believe there's a room for improvements of systolic array layout in other aspects. For example, clock network synthesis, because of this structure is so regular. And so if we look at the figure on the right, so our physical design people can easily recognize this structure. It's pretty much like an H tree, right? But actually, this figure, I got this from systolic array paper by Kuhn and Lesserson. They're not talking about clocking. They're talking about, so for systolic array, you feed the input from boundary. Sometimes you need to do the broadcasting. So this is way to do broadcasting to the data, broadcasting. And also because of the regularity, I believe that can make the routing easier. And also design prediction, and also even like DFM, because there's repeated pattern. Okay, so So here are the conclusions: is that lithography designs are becoming increasingly popular, and here we show that there are a lot of benefit if we have customized solutions, layout solutions for lithography arrays. Okay, and these work are done by my student Jiang Hu, and especially I would thank collaborate with David Pence from student, and the funding supported by NSF and SRC. And before the conclusion, I got permission from the conference chair to spend like one minute to promote MLCAD symposium. It will be Santa Cruz this is September. And if you go to the website, the content has been announced, registration by April, the paper deadline, and there will be industry track, and also we're going to do artifact batch. And that's all for my presentation. Thank you. Yeah.
Thanks, Professor. We have some time. Any questions?
Yeah, very interesting work. How high is the frequency can you get?
Oh, you mean the FPGA part?
Yeah.
I forgot the number. I don't think it is very high, and we just pretty much push the button and run it. We didn't play with it too much, Yeah. I need to double check and get back to you.
Because one tricky part is that if you want to fill up the large FPGA, they now use chiplet technology, silicon, the substrate or interposer. So if you go from one chip to another chip, you have a significant performance buffer that interconnect, even they are facing. So you got to actually have ways to handle that.
We haven't thought about this is necessary. So you mean like one array can be different chiplet?
Oh yeah, if you have a big array, it
Okay.
has to be different.
Otherwise
you only use 25% of it.
Okay, yeah, this is a good point. Then that would be a bottleneck to be considered. That's true. Yeah, thank you.
So that has to be considered.
Yeah.
In fact, I'll talk about it. You have to consider it with a high level design.
Thank you. I'll be happy to learn from you. Thank you. Yeah.
All right, any other questions? Yeah.
And maybe I overlooked something, but how do you get better than the ILP? Is it because the ILP runs into a timeout, or is there some
one reason actually is a timeout. Yeah, right. Yeah, we have like a hard. I think we set like 8 hours, 10 hours of timeout. That's true.
Okay.
Yeah, right. Yes, yeah.
All right, anyone else?
Dr. Hu talked about two specific implementations of PEs, one in which PE is a macro, and the other in which PE acts as a dust. So all of the PE is a dust, right? It's group dust.
So for the ASIC part, we have two different works. One is assume PE is a macro, the other one assume like a P's are dust cells. We have two different works.
Do you see any specific differences or PE benefited one versus the other?
Oh, okay. So yeah, this is a good question. Actually, we also compared these two. Not very fair because the macro one you have a more constrained. Actually, not surprisingly, if you allow all the P cells to be dust, you have a better, variant. Yeah, that's true. This is a good question.
All right, given the time, that will conclude the session on emerging technologies then. Another quick hand for all our speakers.
Okay.